Good morning everyone and welcome to this, which is the fifth in the LimitState webinar series for 2015. I'm Tom Pritchard and I'll be introducing you to our other speaker, Matthew Gilbert, shortly. Today's webinar is the assessment of concrete bridge decks using LimitState SLAB, and it's going to introduce you to the technology behind our Yieldline analysis software, LimitState SLAB, with a particular focus on bridge deck analysis. The first section will be delivered by Professor Matthew Gilbert, and then I'll take over with some examples demonstrating how the software can be used for a number of different bridge analysis situations. The main section of the webinar will run until approximately 10 AM UK time, and we will have about 10 minutes at the end for questions, which can be posted at any time via the chat functionality that's present in the webinar interface in front of you. While we try to get around to as many questions as we can, sometimes this isn't always possible, so we do apologise in advance if we're unable to get around to yours. We do, however, follow up on any unanswered questions after the webinar is finished, and you can also get in touch with us at any time, either through the telephone or via info@limitstate.com. So without further delay, our first speaker today is Professor Matthew Gilbert, and I'll now pass you over to him.
Thanks very much, Tom, and thanks very much to everyone for joining us today for the webinar. Okay, my first slide shows some Yieldline patterns, all the Yieldline patterns identified using LimitState SLAB. However, the two Yieldline patterns on the left-hand side are traditional sort of textbook style Yieldline patterns of a sort that you probably will be familiar with. The Yieldline patterns on the right are much more complex and clearly would be much more difficult to identify via hand. The key thing is LimitState SLAB software is general and can identify Yieldline patterns whatever form they might take. And the next slide just shows animated views of these same Yieldline patterns to aid visualization and make it much more easy to see exactly what's going on, what the mode of response is. Okay, so before I get into the webinar proper, just say a few words about LimitState. It's actually University of Sheffield spin-out company, spun out 2006. The focus of the company is on commercializing academic research, so methods developed in the university and making those accessible to practitioners. And we're focusing particularly on providing ultimate limit state analysis and design software which incorporates novel optimization methods and creating software which is quite different normally to traditional software applications on the market. We're a commercial enterprise, so we're able to fully support applications and also make sure that they're easy to use in a way that the university wouldn't be well placed to do. And also we ensure that software is robust and properly validated. So the existing product portfolio comprises 3 core products: LimitState Ring for analysing masonry arch bridges, LimitState Geo for modelling geotechnical constructions, and LimitState SLAB for concrete slab analysis, which is clearly of interest today. Software is now used widely in the UK and also in 30 countries, actually over 30 countries worldwide. And the next slide just gives you an indication of some of the companies who are using the software, so from quite small companies, local authorities, to large consultants and contractors, so big names such as AECOM, AME, Arup, Balfour Beatty, etc. Okay, so just a bit of background, why we are doing what we're doing, what our motivation is. If you step back and look at the big picture, linear elastic analysis is now convenient and mainstream. So what I mean by that is that we can apply linear elastic analysis to problems of any geometry very, very easily, get results rapidly. However, the same can't be said for rigid plastic analysis. So the rigid plastic analysis tools which were developed in the mid part of the last century have largely stayed as hand-based tools. And our feeling is that engineers would benefit immeasurably from unfettered access to computational rigid plastic analysis techniques in the same way as they have full access to general purpose linear elastic tools. What do I mean by rigid plastic analysis? Well, If we consider a body or structure, what we're typically doing is we're neglecting initial elastic strains, and we're saying that actually, and the most important thing from a collapse perspective is the plateau, and so we assume no deformation prior to collapse, and then perfect plasticity at collapse. So clearly it's a simplification, but it's a simplification which is reasonable in many cases. And the benefits of this approach for ultimate collapse analysis is that from a design perspective, you tend to find that you can design more economical solutions for your clients. And from an assessment perspective, which is clearly of interest today, using these techniques, we can often reveal hidden reserves of strength. So another view of the current situation as regards collapse analysis tools. Typically, we have two very different types of tools available. We have very simple hand analysis solutions which potentially are incorporated in a spreadsheet, or a simple software application which provides a nicer look and feel, but is still at its core a very simple hand analysis type approach. So that's one extreme. At the other extreme, you have advanced methods, for example, non-linear finite element-based methods, which require significant numbers of input parameters, expertise, and normally time-consuming to operate. And so there's quite a large gap between these two types of tools. And we as a company, and also the research group at the University of Sheffield that we work closely with, have been focusing for some years on filling that gap with mainstream numerical rigid plastic analysis tools, and applying those tools in a variety of different domains. So for example, geotechnical engineering domain, applying it for masonry arch bridges, and of interest today, applying it to concrete slab analysis. Okay, so moving on to the Yieldline method. It's long established method, originally devised in the middle of the 20th century, with Johansson being the primary developer of the method. Typically, what you would do if you're doing a hand-based Yieldline analysis is that you would choose a mechanism by hand. You then equate the internal and external work for your chosen Yieldline pattern. And what you would do if you're doing an assessment is you would try to find the multiplier on a specified pressure load or point load, whatever the external applied loading was, at collapse. The caveat is that if you choose the wrong mechanism, then you will get an unsafe, unconservative indication of the margin of safety of the slab. So what you need to do is try a variety of different mechanisms, and typically, if you're doing this by hand, you would try a fair number of mechanisms, but you clearly wouldn't have the time to try every conceivable mechanism. So in terms of pros and cons, pros, Yieldline method provides a simple means of directly estimating the collapse load. From an assessment perspective, you can get a more realistic assessment of capacity than elastic methods for existing slabs. Cons, it's non-conservative if you choose an incorrect mechanism. Also, it only considers flexural failure. It doesn't consider, for example, shear failure, and it doesn't give you any indication about deflections prior to collapse. So, as I mentioned, it's developed in the mid part of the 20th century. It was quite popular, certainly amongst researchers in the 60s and 70s, and there was renewed interest in the 1990s and early 2000s. As an example of this, considering concrete bridges. The Cobras program was developed by Middleton at the University of Cambridge. Basically, this provides a library of potential yield line patterns, and when you analyze a given bridge, the software will test each of these potential failure mechanisms and identify which is most critical and give you an indication of the hence the margin of safety for the bridge under consideration. When the software was applied to existing highway bridges in the UK, it was evident that many appeared to have significant reserves of strength. So here we've got on screen 21 bridges. The red lines indicate the elastic assessed capacity. The green lines indicate the plastic or yield line assessed capacity. And as you can see, that a significant proportion of the bridges which were identified as being inadequate in terms of capacity via elastic methods are identified as being perfectly adequate when plastic methods or the yield line method is applied. So the outcomes of that work was that the yield line method can identify hidden reserves of capacity, and hence it could result in very substantial savings to bridge owners. However, only a limited number of failure mechanisms were considered using Cobras, and when the geometry gets a little bit more complex, critical yield line patterns are often not obvious. And so there's a concern in practice that the critical yield line pattern might still be being missed. And on the right hand side of this slide, we've actually got an image of a floor plate in a building, concrete slab floor plate with internal columns, and we can see in that case the failure mechanism is very complex. Perhaps most bridge failure mechanisms would be slightly less complex than that, but still there is a concern that the critical failure mechanism might be being missed with a simple tool of the sort that was a simple approach of the sort that was adopted in Cobras. On the other hand, as we mentioned, moving to nonlinear finite elements, for example, is expensive in terms of time and operator expertise. So the ideal scenario would be to automate the yield line method, which is what we've focused on doing. What we've used is a technology called discontinuity layout optimization, or DLO. So this provides a rapid and direct means of identifying the critical yield line pattern. The technique was published in a journal paper in well-known science journal, Proceedings of Royal Society A, last year. And it turns out, when you use DLO, the problem of finding the critical yield line pattern is a simple linear optimization problem, which modern PCs are very well equipped to tackle. In terms of how it works, if you imagine you've got a slab, so for example a square slab with fixed support, for example, first step is that you populate that slab with nodes. Typically we have a uniform distribution of nodes. We then interconnect those nodes with potential yield lines, and then we use optimization to find the critical subset of yield lines at collapse, i.e. the critical yield line pattern. The more nodes we use, the more accurate the solution, and effectively if we have a very large number of nodes, we get solutions which for all intents and purposes exact. In terms of the mathematics, what we're doing is we're minimizing energy, and for example minimizing the energy associated with the internal work done along the yield lines. So that's the sum of the length times the moment capacity times the rotation of all yield lines in the slab, subject to nodal compatibility constraints, which we'll look at in a couple of slides. And finally, using the principle of virtual work, we apply unit displacement constraint, which takes account of how the live load is distributed across the slab. And as I said, the key thing is it's a simple linear optimization problem. So nodal compatibility, if we zoom in on the node at the bottom left of a slab, then what we need to do to ensure nodal compatibility is that the rotations at yield lines, the relative rotations at yield lines, sum up to 0 if we go all the way around the node. And the two equations you can see actually relate to resolving those rotations in the x direction first, and secondly in the y direction. So it's a simple linear constraint for each and every node in the problem. Okay, so conclusions from the point of view of automating the Yieldline method. Lack of a general implementation has limited usage in recent years. That's now been addressed via the use of discontinuity optimization. Linear optimization problems are easy to solve. Complex mechanisms such as fans and the like can be automated, can be identified automatically, and the LimitState software is clearly now available. But before I finish my part, what I'll do is I'll just take you through a very simple example using the LimitState SLAB software. What I'm going to do is I'm going to just set up an empty project. So in other words, a sort of blank canvas. I've got on my screen now a grid, so I can use that grid to draw simple slab geometries. So what I'll do is I'll, for example, create a relatively simple geometry. Okay, so there's my slab defined. I'd like to apply a load. I can apply a point, line, or pressure load. I'll apply a point load, let's say right to the middle of the slab. I can choose the magnitude of that load. Let's just say let's say a magnitude 2. And I can switch off my grid and I can select my boundary conditions. So if I choose the if I zoom in and select the boundaries, actually I'm going to be on select mode. Click select mode there. So I've chosen that one. Choose that one. So I've chosen both boundaries, and I can set those to be, for example, simple. So I've now got slab geometry, support conditions, loads. The last thing to do is to define the capacity of the slab and the material properties. So I can go to Tools, create new slab definition, and what I can do is I can select the moment of resistance in 2 directions, either at in this case angle 0 or angle 90 degrees, but I can actually change those angles so I can have model skew reinforcement if I want. For now, I'll keep things simple and just use the default values, and now I can drag and drop that slab definition onto my slab. And I can now click the green button here to analyze the slab and end up with something extremely simple. And I can animate that so you can very easily see the simple mechanism involved. What I could do, however, is change those material properties. For example, here I've got equal hogging and sagging moment of resistance. Very often you would have differences. So for example, if I didn't have much top reinforcement, I would have a lower hogging moment capacity. So I can, for example, set the hogging moment of resistance to be 0.1. So that's 1/10 of the sagging. And if I solve again, then I get a slightly different mechanism. And you can also see I get a solution here. Now the solution in the output pane gives me an indication of how much bigger my load needs to be in order to cause collapse. And I mentioned earlier on that if I use more nodes, then I can get a more accurate solution. So I might want to increase the number of nodes, so choose a fine nodal density in order to get a better solution. And what I've got now is a solution that was 1.4738. It's now gone down to 1.472. And you can see it's a slightly better defined failure mechanism. And again, I can animate that in order to see how that failure mechanism will work in practice. Still a relatively simple failure mechanism, but the key benefit of this being general software is I can, for example, add real-world features. So let's suppose I needed to have a cutout in the slab for some reason. It needs to make some modification to my bridge. Then what I can do is I can select the area to be cut out. I can just simply delete it, and I can simply solve again. And I can see what effect that has on the critical failure mechanism and on the adequacy factor at collapse. So we can see actually that that's changed the adequacy factor from 1.472 down to 1.2477. And again, we can look at the mode of response, and we can animate it to get a very good indication of what the likely mode of response of this bridge would be. Okay, so that's hopefully given you a good indication of how the Yieldline method has been automated and how we've gone about implementing that in LimitState SLAB. I'm just going to hand you over to my colleague Tom Pritchard now, who's going to talk you through setting up bridge example problems.
Thank you, Matthew. As mentioned, what I'm going to do now is actually take you through a few different example problems, starting with a very simple slab with just an axle load on it, and then working up to a more sort of complex slab mechanism with different locations onto it. So for the first example, what we'll be looking at is, as I mentioned, a simple slab with an axle load on it. And in order to generate that, we'll just start again from an empty wizard. And all I want to do now is actually just draw on the rectangle. The easiest way of doing that is just to define something with an arbitrary geometry and then select it. And in the geometry editor on the right hand side of the screen here, you can see that you can then change the different on the right hand side of the screen, you can change the different vertex coordinates. So that's just what I'm going to do now. So you can see that our slab is going to be about 7.8 by 5 meters. And so I click apply, size and shape of the square has changed. What I'll actually do is, if I go to the draw settings, I can auto calculate the extent of the grid, and I'll also just make it a little bit finer as well. And in that way we can snap to the different places when we need to. So we've got a geometry in there. The next thing we need to do is set up the boundary conditions, and again that's very easy. All I'm going to do here is use a rectangle select tool to select the top and the bottom boundaries. In the right hand side here, you can see in the property editor, the drop down, we've got 4 vertices and 2 external boundaries selected. Obviously we're only interested in what's happening on the external boundaries here, so if I select that, then the option to change the support type appears, and we've got the usual 3 fixed and simple support types as you'd be familiar with from Yieldline analysis, and also a symmetry boundary condition which you can apply, and it will basically assume the same on the other side of that boundary. So it's very useful if you've got something like a square slab and you want to just analyze maybe a quarter or an eighth of it. You can use symmetry boundary conditions to then simulate the full model. But for this case, all we're going to do is apply some simple supports to the top and the bottom. And you can see here single hatching, it's obviously signifying that that's what's been done. So we have a geometry, we have some boundary conditions. The next thing to do is to define some mechanical properties for our slab. The way to do that is, if you right click in the slab definitions explorer here, you can see we've got the option to create a new slab definition, and that brings up this menu here. So we'll give it a name and a color. I'll just choose something a little bit different to what's already in there as the built-in definitions, and then obviously we've got first and second direction rebar properties in both sagging and hogging. So for this, what we want is some reasonably realistic material properties. So we'll go for 120 kilonewton meters per meter for the sagging, and a little bit less hogging reinforcement. And in the second direction, which is slightly less important in this case, sagging of 15 and hogging of 2. We'll leave it as reinforcement on a 90-degree grid system, and then for the thickness we can say 0.35 and unit weight of 24. Now the thickness and the unit weight, although we've entered them here, won't be taken into account by default, but you can later in the load case dialog actually specify self-weight loading from the slab, and if you do that, then these two factors here will be taken into consideration. So we've made our new slab definition. Click OK. You can see it appears on the left hand side here, and then we can drag and drop it onto our zone. Similarly, if you wanted to change something, you can click on the zone itself, and then in the right hand side in the property editor you can see it says slab definition 1 assigned. If you click in that field and click change, then a list of all the available slab definitions appears, and you can select the one that you want. So we've got geometry, we've got boundary conditions, and we also have now our mechanical properties. The last thing that we need to do is apply some loading. In this case, what we're going to do is use an 11.5 ton single axle load vehicle, such as you might find in a code of practice as one of the sort of default assessment vehicles that you need to apply to your bridge in order to check the capacity of it. If we click up here, there's a load case manager dialog icon. What we want to be doing, you can see we've got load case 1, and it's a combination of a partial safety factor set and also some loading. At the moment, the partial safety factor set is unity, and we have no loading applied. Obviously we need to change that, and the first thing we want to do is actually make our vehicle. We're going to make it out of 2 point loads, each sort of signifying a wheel load. So to do that, we just select add new, and instead of it being called point load 2, we shall call it 56 kilonewton wheel load, and assign it a value of 56 kilonewtons, which is half of 11.5 tons. Change it to a variable load type. Obviously you can see here we've got permanent, variable and accidental loading, so things are couched in a sort of Eurocode terminology, but that doesn't mean that you are tied to actually using Eurocodes for your analysis. It's basically using it as a convenient way of understanding what's going on and being able to apply your partial safety factors, but in no way do you actually need to stick to Eurocodes for your analysis. So we've now defined a 56 kilonewton wheel load. Click OK, and it becomes available for us to use as the point loads. So we need to apply 2 of these in 1.8 meters apart to signify our 11.5 ton single axle. And if I click the change button here, where you can see if I put the grid on, we can now select a point for our first of our point loads. So the first one I'm going to do is just add it somewhere in the middle, and you can see we go back to the load case manager dialog and the position has appeared. What we actually want to do is I'll try and move it more towards the middle, so I'm going to make it at 3.0, 2.5, and then we'll add another one, and we're going to put this one at 4.8, 2.5. So if I OK that and then click on this icon here, you can see that now we've got these two pink circles which denote the 2 point loads. Again, if I wanted to change the position, I could go back into the locate dialog, or you can select them on the screen and you can see here that the X and Y positions become available within the property editor. So we've got the geometry, we've got the boundary conditions, we've got the material properties in terms of our slab definition, and we've also now got some loading. The last thing we need to do is just apply a partial safety factor to it. So we want to see whether or not our slab is safe given the applied loading that we want to put on it. So we'll make a new partial factor set and we'll call it my code, for example. It could be one of your own choosing, obviously. Now we've got variable point loads on there, so the thing we need to factor is the variable there, and I'm going to put a factor of 1.5 on our point loads. So that means that before the analysis starts, our point loads are factored up by a factor of 1.5. So when we solve, what we're actually looking for is an adequacy factor in the output window here of 1.0 or above, and that would signify that the slab is able to carry that amount of loading according to that partial factor set for those particular material properties. So if I click solve now, you can see that it very quickly runs through the analysis, and our adequacy factor on the applied load is 2.94. So for that partial factor set, we can see that our slab is very much safe for carrying that load. Obviously, if you were doing some design work, what you might want to do is then go back into the slab properties and change the MP values and go away and then design your reinforcement scheme to fit that, obviously, because we've got quite a high adequacy factor. You want to be maybe pushing it further down towards 1. So once we've done this, you can animate the solution to get a better idea of exactly how the slab responds. You can move it around, have a look at it from different angles. Also, if you go to analysis and report, you get a report that details all the different parameters that you've put into it. You can choose the different sections. Once you click OK, it will generate the report that you can then save into a few different formats for use later on. So that's how you do a basic slab analysis using the software. Obviously, some things are slightly more complicated than that, and we'd also want to be moving our loading around the slabs to see what the critical case may be, and that's what we're going to move on to next. So if I just for a second bring up the presentation again, you can see here what we're going to be looking at is the case of an irregular flat slab, which is actually a verge. It's based on the real case of a verge slab on the road, at the edge of a road that was then covered over with a bit of fill and some tarmac, and is now actually being used as the middle of the highway. Obviously, this sort of repurposing required the local authority to get a consultant to look at whether the slab was sufficiently reinforced to be able to be utilised for this new purpose, and check that it was okay to take quite a large vehicle wheel capacity. So what we've got is this irregularly shaped slab. The reinforcement is on a 90-degree grid system aligned to the bottom boundary, and the vehicle that we're going to look at here, which is identified as the one that they wanted to actually check it for, is 4 wheels with the standard 1.8 meter wheel spacing across an axle, and then 2 axles spaced at 2.8 meters. And the consultants had determined that the loading for each wheel was 82 kilonewtons, so quite a high loading. Also, there's a pressure load from the tarmac and the fill on the top of the slab of 2.62 kilonewtons per meter squared, which would need to be taken into consideration. So, similarly to the first example we looked at, it should be quite easy to set this up by hand rather than requiring us to use an import of a geometry, which we'll look at in the next example. What I will do is go to the draw settings and again stick it on auto calculate and change the minor grid line intervals. So basically that will resize the grid depending on what solids I've drawn on there, and also give me a finer grid so that I can place things more accurately. So the easiest way to do this is, again, like we did in the first example, is just to draw a rough approximation of our problem. So I'm just going to draw a regularly shaped slab. Then we can see here in the geometry editor we can change the vertex positions, so we can look very easily, and we go to this one should be 0, 1.672, top right should be 6.207, 4.431, bottom right should be 6.2070, and then the bottom left should be 0, so 0.7850. So there's our slab geometry. The next thing we need to do, as before, add some boundary conditions. And if I just bring up the PowerPoint again, we can see in this case the slab is supported along the bottom, left and top sides with a free edge on the right here. So if I hold down Control, I can select all three of these boundaries. And then the property editor, set the support type to simple. So there we go. Next step is make a new slab definition that we can then apply. So if we call it slab 1, change the colour, and then add the material properties. And the consultants in this case had determined that the sagging moment capacity in each direction was about 90 kilonewtons per meter per meter, but the hogging was absolutely nominal at 0.1. The slab thickness, I'm going to put in the real values but not actually take them into consideration. And then again just apply that slab definition to our solid. So now we've got a geometry, boundary conditions and a slab definition applied to it. The last thing we need to do is add the loading. So again we can open the load case manager, and as I mentioned in the introduction to this section, there's a pressure load on it which we're going to call super, and that pressure load was 2.26 kilopascals, and that's a permanent load because it's the black top and the fill underneath. So now we can add that to our solid, select OK, you can see that it exists there. So we've got the pressure load. What we also need is the vehicle loading, which will be 4-point loads at the 1.8 and 2.8 meter spacing on that rectangle. So just create a new one. If you remember, the consultants had decided that it was 82 kilonewtons per wheel, so that's what we'll call it. Give it a value of 82 kilonewtons and make this variable, so then if we do change things in the partial factors, it will be scaled accordingly. So you can either select from the drop down and then change the position on the screen, and that's if you've got a nice grid system, you can just snap to wherever you want, or in our case what we'll do is we'll just type it in. And what we're going to do is going to traverse our vehicle from the right to the left of this slab. Also, you'd want to be doing it from the bottom to the top and maybe also diagonally across, but we're just going to do the first set of cases for this. So for our wheel loading, the first point I want to be at -2, 1. Add another wheel at -2, 2.8. Then the third and the fourth will be 0.8, 1, and lastly 0.8, 2.8. So if we get rid of the grid and then show the loading in the loading dialog there, you can see that we've got the 4 point loads which represent our vehicle, and also a red outline around the boundary of the slab just to signify that we've got pressure loading on there. And obviously what we want to do now is move that vehicle across from the left to the right of the problem, and we do that by going back into the load case manager. What we do is select all of our loading, and then at the bottom here in the drop down we copy that, and you can see here that we can then provide an offset and a number of copies and generate the different load cases according to that. So what we're going to do is, for the sake of time, I'm just going to add 6 extra load cases at quite a wide spacing. What you might want to do is reduce the number of reduce the spacing distance and increase the number of load cases, but for our purposes what I'm just going to do is 6 copies and move it by 1 meter each time. Here we've got a warning just saying that self-weight and pressure loads don't offset. Obviously if the slab pressure load was to be moved by the same offset as the vehicle loading and the point loads, then we would get an answer that wouldn't be credible, and that warning just tells us that. So you can see now we've got the number of load cases, and if you look at the position of our point loads at the bottom, you can see that it just moves across by 1 meter in each case. So there we go, we've set up the 7 load cases. So I'll OK, and now you can scroll through them using this roll box at the top. So the last thing we want to do is check what the nodal density is, and I'm going to keep it on medium just because we've got a number of load cases here to solve. What you might want to do is either identify the critical load case and then solve that on its own at a higher nodal density, or if you're really interested in all the different failure mechanisms, obviously you can set the nodal density to a much higher value and then run the entire analysis all in one go, but we'll keep it on medium. So I click solve, and what you'll see is at the bottom here we're moving between the tabs for each of the load cases, and associated with each one is a slightly different failure mechanism. And once we see the solution, I think we're just coming to the end of load case 3. We get an idea of what's happening, and with the vehicle moving to the right, the adequacy factor is actually reducing slightly in each case. So, and it makes sense because we've got this free edge towards the right hand side of the problem here, so you'd imagine that as the vehicle approaches that the capacity of the slab would be reduced. And also actually for load case 4 and load case 5, you can see that the failure pattern is quite different to the ones that we got in the first few load cases, where we were just getting this circular fan type mechanism around one of the point loads. Now we're getting more sort of total failure of the slab and involving this free edge. Right, so we can see here for load case 6, the solution value is much lower than it was in any of the previous 5. So I guess the thing to do is see what the adequacy factor for load case 7 is, and that's 4.5, and you can see the software has told us here that the minimum adequacy factor on the applied load is 1.36, and that's for load case number 6, and in the viewer window here, that's the case that's been identified and shown to the user. Again, what we can do is animate it and rotate it just to get a better understanding of what's happening. If I reset that back to 0, we can also do, if you're interested in what's happening for each of the other load cases, you can move through them. You can also again turn on the display of the point loads just to give you a better idea of where the wheel loads are in each of these different situations. But as you can see, we've very quickly set up an irregularly shaped slab problem using sort of real life loading cases and determined roughly where the critical load positioning is for this particular case. As I said right at the beginning of this example, though, what you would want to do afterwards is then start trying different orientations of the vehicle. Obviously this is going from left to right, which is probably not the most realistic of cases. You maybe want to go from bottom to top or even diagonally across. So we've had a look at a very simple slab with just a single axle loading. We've had a look at an irregular shaped slab with a moving vehicle load on it. The final example that we're going to have a look at is something that's slightly more complex than that. And that's a beam and slab bridge deck. Now this is based on an example that's provided in Jackson's thesis from Cambridge that's published in 2010, and I believe in turn that's actually based on Hazel's testing of a scale model of a beam and slab bridge deck from a few years earlier. And you can see what we've got is some simply supported longitudinal beams, which are obviously the thin portions here, which correspond to this in the cross section, and they're separated by a much thinner slab deck. So it's something you may come across in real life. The slab is quite lightly reinforced, whereas the beams have much more substantial reinforcement, certainly in the bottom. So the geometry for this is sufficiently complex, I would say, that one of the best things to do would be to actually import the geometry from a pre-existing DXF file. So what you can do, if you've got something that you already have as a drawing, you can save that as a DXF and then import the geometry into the software. You can see that lines forming closed loops will import solid geometry objects. So basically you can get the DXF import to do half your job for you, and these are just the two layers to import. If I click OK, you can see that the lines that were within my DXF file have now been turned into separate solids within the software. So that's given us a jump start on it. So we have the geometry, and it's a case as before, just going through and setting boundary conditions, which again in this case will be simple. And then going on to define the material properties. So you'll see, if I right click in the Slab Definition Explorer, that you do have the option to export and import slab definitions. So if you did have a particular one that you use quite often, you can save that, and it'll save you the trouble of having to go through the process of defining it again for your other projects. You could just import it. But for this one, we're just going to make some new ones. So for the first part, we need slab. I'm going to make that a lovely yellow colour. And as we said, the slab is very lightly reinforced. So we're going to have quite low reinforcement properties. Again, we'll just keep the reinforcement orientations at 90 degrees to each other. And we'll put the actual thickness and unit weight of the concrete in there. But obviously this isn't going to be taken into consideration unless we set the slab self-weight to be true in the load case manager. So we've got a slab, do the same for the beam. I'll make that dark blue. So for the first direction, I'll have 150 for the sagging and 120 for the hogging. The second direction, which is across the slab, needs to be stronger, so 500 and 300. And the thickness obviously is quite a bit higher, so 0.204. But again, the unit weight we'll call 24. So now we've got in the Slab Definition Explorer slab and beam slab definitions. What we can do is drag and drop the slab, but we've got quite a lot that we want for the beam, so we can select all the different zones, and then in the right hand side where it says 0 slab definitions assigned, just click in there and change and make that into the beam. So there we are, we've got slab and the beam all set up, got the material properties, the geometry and the boundary conditions. So now what we need to do is apply some loading, and I suspect if I look at the grid, yes, it's quite coarse. So what we need to do, if I go for draw, settings, do what we did previously, just make it 20 and 20. So now you can see that the grid is a lot more fine-grained. And what we want to do is apply in the center of these two squares here just a unit point load. They can both be part of the same load case. So if I click in the middle of there, you can see load, use existing unit point, which is a built-in point load. You could create your own if you wanted to, and then the load case that is part of, so the position, the action type, which is unfavorable, and adequacy true just means that that's one of the loads that we're going to factor up in order to determine the adequacy factor for our solution. So we click OK. Then we do the same again at the center of the other beam. Again, unit point, position, and it's going to be in the same load case. So we click OK. Turn off the grid, and you can see that our entire problem is now set up. Now, one of the things that we have mentioned previously is that in the property editor you can set different values of nodal density. In this case, it's a single load position. We're not really doing any scoping. We're just going to see what the answer is. We want quite an accurate answer, so I'm going to choose the very fine option. And if I go to analysis and preview nodes, you can see now that there's quite a fine spread of nodes throughout the entire problem. So we've just come to solve that. We can see if I bring up Jackson's original failure mechanism, you can see this failure mechanism and ours are very similar because it involves failure of the second slab section from the left plus a straight line through these two beams in the first slab section. But the mechanism for this second slab section is actually quite a lot more refined than in Jackson's original. Again, if we animate, you get an idea of how the problem is failing, and that's about it really. So we've seen very quickly 3 different cases of how to set up and solve different types of bridge slabs. So we've got the simple rectangular slab just with a single axle loading. We've got the more complex slab geometry with a moving vehicle, and we've also got this beam and slab arrangement here with, in this case, just a single loading on it, but again you could move the load across if you wished to. So that finishes the example section. I think if we move on to see if there are any questions, I'll just open up the dialogue and see if we have any. We do. With multiple patch loads on an irregular slab panel, will the program search for the most critical position of the loads? The answer to that is yes. I think, as you saw in the second example that we went through, you can set up multiple load cases anywhere on the slab that you like, and when the program is analysing it, it will go through and determine out of those which is the most critical, and then it will display that and the associated adequacy factor and mechanism to you after the analysis has concluded. Just see if there's any more questions. Can you take into account skew reinforcement? Yes, certainly. What I can do is I'll just make a rectangular slab. I think Matthew may have gone through this very briefly at the beginning of the webinar, but we can see here, if we make a new slab definition, we'll call it slab. OK, and I'll apply that and solve. You can see we get this sort of standard expanded fan type failure mechanism for this problem. But then if we go back in and change the orientation of the reinforcement, so instead of having the MP acting at 90 degrees to the horizontal, has it acting at 45 degrees and 0 degrees. Solve again. You can see that the geometry of the failure mechanism has changed quite considerably. I mean, the solution has actually reduced very, very slightly in terms of adequacy factor, but the layout of the yield lines has changed quite markedly. So then you can, say, take into account skew reinforcement. If I set that back to 90, we've just had another question come through. Can you model columns? There was some in the example building slab in the introduction. I'll just bring up that picture again for you. So here we are. You can see this building slab here, which has a number of external columns as well as internal columns. So the question is, I guess, how can you model those? It's very easy. If I turn the grid back on, all you need to do is find the place where your column is, draw a square or a rectangle accordingly, or any shape you wish really. Delete the material from the inside of it.